We've got a stack of source material today that is, well, it's pure competitive adrenaline
Oh, absolutely.
mixed with some really cutting-edge machine learning,
Welcome back to the deep dive. Our mission today is to tear through the notes for the virtual robot race.
which is this amazing AI learning platform. It's built for speed, for algorithm development, and, for getting results fast.
And that's the whole hook, right?
Yeah, the whole mantra in the notes is AI learning platform with easy, smart, low cost. And that low cost part is so key. You don't need expensive hardware or anything.
It's all simulation.
All high fidelity simulation and just pure code competition. It's fantastic.
And it lets you use Python to develop and race your own AI algorithm, which is, great for anyone wanting to learn the nuts and bolts of this stuff.
For sure. But we have to say it right up front. This
Oh.
is brand new.
It really is. The official status is beta released en Nobu.
Right. Which means the community is still shaping it. And for now, that beta is only for Windows 11. That's the starting line. Perfect. So for this deep dive, we're going to explore that core structure, the 4 control modes.
The step-by-step learning philosophy.
Exactly. We'll get into the setup, which is super fast, and really emphasize why this whole thing is a competition that needs your input, your code, right now.
I think that structure is the genius of it. It really anticipates the learning curve. It manages the complexity, so you're not just thrown into PyTorch from the get-go.
You build up to it.
You move naturally from manual control to, sophisticated neural nets.
Okay, so let's start at ground zero, the manual stuff. There are 4 control modes, and the first one is keyboard mode.
That's modem 1.
Right. This is your manual input. You're just getting a feel for the track, the inertia, all of that.
And it's doing 2 things at once. It's not just for manual driving. It's also your very first data generator.
Yes. Every turn you nail, every straightaway, that's all data you can use later.
Which leads you perfectly into mode 2.
Table playback. So modem M2. And this is a huge leap conceptually.
It really is.
You go from real-time input to sequenced data-driven control. You're just editing a CSV file.
And you're basically a control engineer at that point, just playing back commands. And the precision they mention is pretty remarkable.
The 50 milliseconds.
Yeah, the one-time ID clocks in at 50 milliseconds. That is a very, very tight window for commands.
And that implies so much, doesn't it? If it were slower, say 500 milliseconds, you could just react to everything.
For sure. Simple reaction loops.
But at 50 meters, you are forced to think ahead. You have to be predictive, not just reactive.
Exactly. It forces you to think about high-frequency control decisions, which is exactly the challenge in real-world embedded systems. You have to be fast and efficient.
And to do that, you're controlling just 2 parameters in that CSV file. Drive torque.
Which is +1 for forward, -1 for reverse.
And steer angle. +1 for right, -1 for left, 0 for center. Simple inputs, but the sequencing is where it gets complex.
And there's a pro tip in the source notes for this, for making good playback data.
Oh yeah, the part about metadata.csv.
Exactly. They tell you to copy data from a good manual run from metadata.csv and put it into input.csv.
But you have to leave something out.
Yes, and this is critical. You have to skip the aid column. That's just tracking info. You only want the raw control vectors, drive torque, and steer angle.
It's a clean data transfer, so you can automate and perfect a good run without having to drive it over and over.
Okay, so now we cross the bridge.
Into actual custom programming.
Yeah.
Rule-based control, modem and clone 3. The project team called this one of the core control modes.
And it is. This is the developer's sandbox.
Yeah.
It's asking you to stop playing back old moves and start writing your own logic.
Probably in Python.
Almost certainly in Python, yeah. To control torque and steering based on what the car is seeing live.
And you get new data streams here. You're not just flying blind. You get RGB and SOC.
Let's break those down. RGB is, red, green, blue. It's visual input, a camera.
So your algorithm can see the track.
It sees the track, the lane lines, obstacles, everything. This is where you can start doing some classic computer vision.
And SOC. That's state of charge, battery life.
Right. And you might think, why does battery life matter in a simulated race?
Because it adds a whole new layer.
It really does. Because if you just want speed, you might be tempted to just slam the torque to max to 1.0 everywhere.
But you'll run out of juice.
Exactly. A smart algorithm sees the SOC data, sees the battery depleting, and it has to modulate the torque to make sure it can actually finish the race. It becomes an optimization problem.
It's not just about speed, it's about efficiency under pressure.
And the sources give a little hint here. They say, I recommend to work with Claude Code for this mode.
That's a direct challenge, isn't it? They want to see some sophisticated, high-level conditional logic.
Yeah, mode 3 is the real proving ground for your logic before you even think about machine learning.
Which brings us to the finish line, AI mode, Modinum 4.4.
The big one.
This is where you race your algorithm by using PyTorch.
And using PyTorch means they are serious about deep learning. But the brilliant part is how the other modes feed into this.
All that data you generated.
Every run, even the crashes, from keyboard, table, or rule-based modes, that's all training data. You harvest it, you feed it to your PyTorch model, and you deploy that neural network right back into the car.
And they even say you can mix them. Users may mix AI and rule-based control.
Which is so important for optimization. I mean, and rule-based is great for simple stuff, like staying in your lane.
That's deterministic.
Exactly. And AI is better for the nuanced stuff. So you can combine them, use rules as like a safety layer for your neural network. It's super flexible.
Okay, so this is where it gets really, really interesting. Because the platform is in beta, we're seeing people try to leap straight to this high-level stuff. And the results are, well, they're telling.
And hilarious.
We saw this clip of a user who took that Claude Code advice to heart. They were trying to solve a really advanced problem in mode 3.
The classic stability issue. Yeah, they were looking at the RGB and SOC data, trying to program what they called critical balance.
I mean, that's high-level thinking right there. They wanted to dynamically adjust steering to prevent oversteering.
Surgical precision. That was the goal. Their GitHub notes showed they spent hours on it, fine-tuning the Python script, trying to make it predictive.
They were going for that perfect drift, that flawless entry into the curve.
They really were. You could just feel the anticipation as the robot started the lap. They thought they had cracked it.
And then the first curve.
Oh, it was magnificent. All that tuning, all that Claude Code sophistication. And the robot still crashed and fell off the track at the first curve.
It was a perfect, spectacular, self-defeating pirouette straight into the wall.
It was beautiful.
I think we have to say it.
Looks like he needs to tweak that Python script.
He really does. But that failure, that crash, that's the whole point of the beta.
Absolutely. It's not a solved problem. It's an open invitation.
And that crash just reinforces that the code is waiting for someone to fix it.
That's why we need you to join the race and fix this code. Your idea might be the one that finally gets that critical balance right.
And to help you do it, the data-saving features are, well, they're critical. You can use all that data from the run to figure out what went wrong.
And the sources point to one file specifically, metadata.csv. They say this file leaves useful information for when.
That's your holy grail.
It is. It has everything. Analyzing that file is how you figure out what went wrong in that crash and what needs to change.
So you've seen the challenge, you've seen the glorious failures, and you know the data's there to help you succeed. How do you actually get in the race?
The setup is, it's designed to be fast. It's really frictionless. Step 1, download the files from GitHub.
And
Then the instruction is literally just click .bat file. That's it. You're up and running.
Okay, but there are a couple of configuration things to know about. There are 2 tiers of settings.
That's right. The first one is for all the big race settings, the track, difficulty, that kind of thing. The second level is for each robot-specific setup.
And a quick beta note here. Right now, it only covers 1 or 2 robot settings. The main settings file is config.txt, right in the top layer of the directory.
Right. So once you're set up locally, the whole competition is about community. And they've laid out 4 clear steps to join.
Step 1, download from GitHub. We covered that. Step 2,
Race your robot, record it, and post that result to X.
and then step 3, the community managers pick up those videos from X and feature them on their YouTube channel.
Yep, that's the hub. You can watch races, analyze what others are doing. And step 4 is communication. That also happens through the YouTube channel.
That social feedback loop is so important. You can see what's working and what's not almost in real time.
For sure. And if you think you've got a winner, you have to set the official flag.
Race flag 1.
That's the one. When you set that, your result is officially sent to the global ranking. It's you saying, okay, I'm competing for real now.
I love this feature for making it easy. If you don't want to mess with screen capture software, you just set Automake Video 1.
And it does all the work for you. It generates the race video so you can just instantly share it on X. You just focus on the Python, the platform handles the rest.
So what does this all mean for you listening? The virtual robot race, right now in beta, is wide open. It's offering this amazing structured path to learning AI control.
It's a comprehensive invitation. It meets you wherever you are. You can start with keyboard mode, refine logic with table mode, tackle algorithms in rule-based mode.
Or go straight for the big one with PyTorch.
Exactly.
This platform is hungry for new code. We need you to download those files from GitHub today, race your algorithm, and post those results on X, even the hilariously catastrophic ones. Get involved.
And here's the final thought to take with you, the provocative thought. We saw that user crash trying to implement critical balance. Your algorithm in mode 3 and 4, it generates this live beta active output. Given that metadata.csv is the key to winning, how will critically analyzing that live stream of data, frame by frame, be the only way to finally understand and stabilize that critical balance where others have struggled?
So success isn't just about writing the code.
No, it's about interpreting the data your code generates in real time. Go find that stability.